Alright, so this is a tutorial on the bottom-up compilation of sentential decision diagrams. This is to be contrasted with top-down compilation, which is covered in a separate tutorial. And here's the agenda. We will talk about 4 topics. We will start by motivating bottom-up compilation and some of the challenges. And then we'll talk about the topic of canonicity, which is quite important for bottom-up compilation. And the third topic is the process of compiling Boolean formulas into SDDs. And finally, we will talk about the SDD package, which is available publicly and implements the compilation methods that we're going to be talking about. The SDD package will also be mentioned throughout this tutorial. And we will start by motivating bottom-up compilation by talking actually about the compilation of OBDDs, which are a special case of SDDs. We will illustrate the process of bottom-up compilation using this simple formula, which is a conjunctive normal form, a CNF, that have 2 clauses. When building an OBDD, we need a particular variable order. In this case, we will use the order XYZ. Bottom-up compilation is conceptually pretty simple. So if you want to compile this particular CNF, which have 2 clauses, what we will do is compile each clause separately, and then we conjoin the 2 OBDDs that correspond to these 2 clauses. And to compile a clause, let's say X or Y, we will first find an OBDD for the variable X, and then another for the variable Y, and then we will disjoin these. So as you can see, bottom-up compilation requires an ability to combine compilations. In this particular case, they are OBDDs. And this is done using an apply operation, which is basically an operation that takes 2 OBDDs in this case and combine them using a Boolean operator like conjoin and disjoin. And later when we talk about SDDs, we will also assume that we have access to a similar apply operation. This is kind of a prerequisite for bottom-up compilation. So let's get started here. We want to compile the first clause, and we start by compiling or building an OBDD for the variable X, or the positive literal X, and here it is. We build a similar OBDD for the variable Y, and now what we need to do is basically disjoin these, and here we get the OBDD for the clause X or Y. We do something similar for the other clause, and we get this OBDD. And now we have to basically conjoin the 2 clauses, and we do that by conjoining their corresponding OBDDs. And here's the final OBDD for this particular CNF. One thing to realize here is that there are some leftover nodes from the compilation process, and these are called dead nodes. They were useful during the compilation process, but they are not part of the final outcome or the final result. So these, in the language of bottom-up compilation, these nodes are called the dead nodes or garbage, so they need to be collected. And that's part of the bottom-up compilation process, is this notion of garbage collection of intermediate nodes that end up not being part of the final result. So if we look at a summary of bottom-up compilation, we realize that it does require this apply operation, and a garbage collector, which is provided by packages that do bottom-up compilation. The 2 challenges here is the following. One of them is, for the case of OBDDs, is we need to have a good variable order, because if we choose a bad order, then we may end up getting a very large compilation, and this is a subject that we're going to discuss in detail later. The other important thing to note here is the order in which we do apply operations. That also can have a significant impact on the efficiency of compilation, particularly the number of intermediate nodes or dead nodes that we end up generating. So one also need to have a heuristic for ordering apply operations. We'll talk some about this later. But just to give an example, here's one CNF from the SAT literature, which has its OBDD has 176 nodes when constructed using a particular variable order obtained from something known as the mince heuristic. But when we try to compile it using the cut package for OBDDs, using this order and a particular sequence of apply operations, we ended up having more than 30 million intermediate nodes. And this again could perhaps be reduced if one sequences the apply operations a little bit differently, but it does highlight one of the challenges that exist in bottom-up compilation. And this particular challenge actually is alleviated when one uses top-down compilation, but this is outside the scope of this particular tutorial. And of course, top-down compilation has its own challenges as well. So if you want to read more about the difference between top-down and bottom-up compilation, at least in the context of OBDDs, then this paper actually discusses that in some detail. Let me now get to the topic of canonicity, because that's pretty important in bottom-up compilations. OBDDs are canonical. What does that mean? If I have a Boolean formula, I want to compile it into an OBDD. Once I fix the variable order, there is only one unique OBDD that corresponds to that particular formula. And for that to happen, actually, the OBDD has to be what the people call reduced OBDD, but the detail here is not important. The significance of this is if I'm trying to compile a Boolean formula into an OBDD of a small size, then all I have to do is find a good variable order, because once I choose a variable order, the OBDD and its size are determined. The same story is applicable to SDDs. They're also canonical, except in this case, instead of a variable order, we need to have a tree structure over variables, which is known as a Vtree. And again, for a particular Boolean formula, once I fix the Vtree, there is precisely one SDD that corresponds to that formula. So once more, if we're trying to minimize the size of an SDD for a particular formula, then that actually becomes a matter of finding the right or the appropriate Vtree, a process that we're going to talk about in some detail later. And once more here, for SDDs to be canonical, they have to satisfy some other properties, and in this case, they're trimmed and compressed SDDs. If you want to read more about canonicity and its role in knowledge compilation, you can consult this particular paper, which appeared in AAAI in 2015. So let me now go to the important topic of choosing a Vtree. So the choice of a Vtree can have a significant impact on the size of an SDD. In fact, the difference could be exponential, as we will see in just a little bit. Choosing a good Vtree could be done in two particular ways. The first one is what we call static, and that is done by analyzing the structure of the Boolean formula before the compilation starts. That is, we usually we abstract the Boolean formula into some kind of a graph and do some graph analysis to find a Vtree, and then we just use that one Vtree to do the bottom-up compilation. The other one, or the other method, which is dynamic construction of Vtrees, which we will focus on in this tutorial, is to choose the Vtree dynamically during the compilation process. So how does this work? So you start initially by guessing a Vtree, perhaps using a static method, and then you start the bottom-up compilation process by sequencing apply operations. And if at some point the SDD size grows too large, then you stop the process and then try to change the Vtree so as to minimize the size of corresponding SDD, and then after that you resume the sequencing of apply operations to try to finish the compilation process. This could happen multiple times, and there is this notion of a trigger which is used to decide when to stop the bottom-up compilation process and then go and change the Vtree, and there are different triggers for doing that. One of the more common ones is to look for the size of the SDD, and if it doubles in size since the last change to the Vtree, then we try to change the Vtree again. All right, so just to give an example of how important the Vtree is, let's look at this particular Boolean circuit, which represents a Boolean function. We have two sets of variables here, x1, x2, x3, and y1, y2, y3. And the circuit itself has two kind of gates, AND gates and exclusive OR gates. So if we want to compile this Boolean circuit into an SDD using this particular Vtree here, then we get an SDD that looks like this. This looks big and hairy, And in fact, this is exponentially sized in the number of x and y variables. But if we use this particular Vtree, different one, then the corresponding SDD ends up looking like this. And actually, this is linear in the number of variables. So here's an example where the choice of a Vtree made the difference between having a linearly sized SDD versus an exponentially sized SDD. If you want to read more about the previous example and this phenomena, you can look at this particular paper, which appeared in AAAI 2012. So now we will talk about searching for a Vtree, the goal of which is to minimize the SDD size. And again, this is typically invoked in the middle of bottom-up compilation when we find that the SDD has grown too large, that we think that the Vtree that we're currently using is not a good one and we want to search for a new one. And to motivate this particular process, I will use first an example of the similar situation but in OBDDs. So again, because this is simpler. Recall that OBDDs are characterized by a total variable order. So if we have n variables, that's basically n factorial orders. And here's a concrete example with respect to 4 variables. In this case, 4 factorial is 24. So we have 24 different total orders and therefore 24 different corresponding OBDDs. And trying to find the smallest OBDD in a sense is a matter of picking one of these 24 total orders. Now the key thing here is the following, is to find a local operation and that will allow us to navigate the space of total orders. And for OBDDs and total orders, that happens to be pretty simple. We can in fact navigate the space of all permutations by simply swapping 2 adjacent variables. So if you look at the very first order here, A, B, C, D, what we did actually is swapped the variables C and D, and then we got the next order, which is A, B, D, C. And in the second one, we went ahead and swapped the variables B, D, and then we get the third order, which is A, D, B, C, and so on. So again, the importance of this is we have one simple operation, which is swapping 2 adjacent variables, which is sufficient to define our search space and to navigate our search space. And we're going to see that we'll have something similar for Vtrees to be able to navigate the search space of Vtrees, but we will need different operations in that particular case. So before we talk about how to navigate the space of Vtrees, we will look at this connection between a Vtree and a variable order. You can think of a Vtree as being a dissection of a variable order. What does that mean? So if you look in this case, we have the variable order A, B, C, D, and you can think of the Vtree as recursively splitting that particular order. So the top node of this Vtree has split the variable orders into 2 components. The left component, which is A, B, C, and the right component, which just contains the variable D. And then for the first component, which is ABC, then we dissect it again, and we keep doing this until we hit individual variables. So we get this particular Vtree. So again, we have a total variable order, and then we have a dissection of that particular variable order. Now clearly, we can do this dissection in different ways, and in this particular case, there's actually 5 different ways in which we can dissect a variable order of length 4, and here are all of the 5 different dissections. And that helps us in counting how many Vtrees we have. So if you want to get a sense of the search space involved here, recall that if we have n variables, we have n factorial total orders. Now, the number of dissections over n variables is this. That happens to be the number of full binary trees over n leaves, which is also known as the Catalan number. If you multiply this number by n factorial, which is the number of total orders, you get the total number of Vtrees that we have over n variables. And if we want to see some concrete numbers, here's an example going from n equals 1 to n equals 6. So for 6 variables, we have 720 total orders, and each one of them can be dissected in 42 different ways, leading to 30,240 different Vtrees over 6 variables. Now, once more, a reminder that the choice of a Vtree can lead to an exponential difference in the size of an SDD. In fact, moreover, the choice of a dissection can lead to an exponential difference in the size of an SDD. That is, for the same particular variable order, one dissection may lead to an SDD of linear size, and another dissection may lead to an SDD of an exponential size. Once more, this is to emphasize the importance of finding a good Vtree when we're doing bottom-up compilation. All right, so how are we going to do this? So once more, you can think of this as a double search problem. We need to find a variable order and we need to find a dissection, but we actually do that using 3 different operations on trees. The first 2 are called rotations. They're classical operations from the literature on algorithms. They're called left rotation and right rotation. And then we introduce one more called the swap. And these 3 alone are sufficient to navigate the space of Vtrees, as we will see next. So let's look first at 3 rotations. If you look on the left, we have a portion of a Vtree. The root here is A, and what we want to do in this case is right rotate that particular node A. If we do that, we get the Vtree on the left. So on the right, sorry. So look what happened here. B moved to the top. It's now the root, and its children has changed, and similarly A went down and its children have also changed. So this is right rotating node A. We can reverse that by left rotating A. So if we go to the Vtree on the right and left rotate A, then we get back the Vtree on the left. Now, interestingly enough, these 2 operations, left rotate and right rotate, are sufficient to navigate the space of all dissections for a given order. One observation here is that rotations do not change the underlying variable order. So if you look in this case on the left, the underlying variable order is XYZ, and if you look on the right, it's still XYZ. So again, rotations change the dissection, but they leave the underlying order untouched. And as I said, there are systematic methods out there that in the algorithms literature that show how one can sequence left and right rotations in a fashion to ensure the navigation of all possible dissections. And here's an example, a concrete example to illustrate this. So what we have here is a Vtree over 4 variables. The underlying variable order is A, B, C, D, and if we look here on the left, this is one particular Vtree, and now we're going to see how we can navigate the space of all 5 dissections using only rotation operations. Again, starting on the left, if we go ahead and left rotate X, we get this particular Vtree. If we left rotate X again, we get this dissection. If we now left rotate Y, we get this dissection. If we now right rotate X, we get this dissection. And then if we right rotate Y, then we go back to the initial dissection that we started with. Now, to be able to also navigate the full space of Vtrees, not just dissections, we would need to be able to change the underlying variable order. And for that, we need the operation of swapping. And this is a simple operation. If you look on the left here, we have the root node A. It has X as the left child and Y as the right child. And swapping A simply means that we flip its children. So now we have Y on the left and X on the right. And if you look at the underlying variable order, we did actually make a change to that particular order. And as it turns out, by mixing swaps with left and right rotate, we can now navigate the full space of Vtrees, not just the dissections of a particular variable order. And this is a simple illustration here showing how we are starting on the left with a Vtree that dissects the variable order A, B, C, D, and doing 3 operations that allow us to eventually get a dissection, but for the variable order A, C, B, D. That is, we swapped the variables B and C in this particular case. Realize that the first and the last Vtree are both what we call right linear, but they differ in the total order that they actually embed. Now, here's an important point. So the SDD package, which implements the final algorithm that we're going to discuss for searching Vtrees and finding one that leads to an SDD that is small, this SDD package does provide support for these Vtree operations, but it gives high-level support for these Vtree operations in the following sense. If we look on the left here, we see a particular Vtree, and if we look at the right, we see the SDD that corresponds to it. Now, suppose the user wants to right-rotate Vtree node 3. There is a primitive for that in the SDD package, but that primitive will not only modify the Vtree as a result of this operation, but it will also go ahead and change the corresponding SDD as a result. So in this case, if we go ahead and do the right rotation on Vtree node 3, we get this particular Vtree on the left, and then as you can see on the right, we now have the one SDD that corresponds to that Vtree. The change on the right is done automatically by the SDD package on behalf of the user as a result of doing this rotation operation. And this is pretty important because that makes it easier to implement search algorithms for Vtrees without having to worry about these low-level details. The other thing that to notice here is that when we did this rotation operation, the size of the SDD shrunk in size. It could, of course, grow in size, and sometimes it could grow very significantly, and the operation itself, the rotation or the swap operation, may take a very long time. Because of this, the SDD package allows users to put limits on these Vtree operations, and these could be time or space limits. For example, you can say, go ahead and left rotate node 3, but fail if it takes more than 2 seconds. And what will happen is if the operation takes more than 2 seconds, then not only will the operation fail, but the SDD package will also roll back all changes that it made and brings back to the user a clean state with an indication of failure. One can also limit the growth in the SDD size. So for example, you can say, go ahead and do the swap operation, but fail if it leads to more than doubling the size of the SDD. So now we're almost ready to start talking about the actual Vtree search algorithm, whose goal is to try to minimize the size of the corresponding SDD. But for this, I need one more abstraction, which is called the fragment abstraction, which even makes it easier to implement the search algorithm, which, as you'll see, we'll be able to explain on one slide once we have introduced the notion of a fragment. Fragment is a portion of a Vtree. Here's what we call a left linear fragment. There's two types, left linear fragments and right linear fragments. So here's the left linear fragment. It just happens to be 5 nodes. 2 of them are what we call internal, the root and the child, and the other 3 are what we call virtual leaves. And the second type of fragment is this, which is the right linear fragment. Again, 5 nodes, 2 of them are internal, the root and the child, and the other 3 are basically the virtual leaves. Now, what's the importance of these fragments? First observation is, a fragment can be in one of 12 possible states, depending on the total order of the virtual leaves and the way that they are being dissected. So if you look here on the upper left, what we have here is a left linear fragment. The underlying order is A, B, C. And if we go and right rotate the root, then we go to the next state. If we swap, we go to the following state, and so on. And in fact, the SDD package provides a fragment abstraction, which is a structure, together with operations that you can apply to this structure. That includes next. So if you construct a left linear fragment, let's say, and you can say next, then it will take you to the next state. If you call the operation next again, it will move you to the state after that, and so on. And you can do previous, so you go to the previous Vtree in a fragment. You can even go to any particular state. So, and if you're, let's say, at state 7, you can say, let's go back to the initial state of that particular fragment. Now, the importance of this abstraction is it makes it significantly easy to implement local search methods for finding Vtrees, as we will see next. So here's how the search algorithm works, and this is the one that's implemented in the SDD package. It's a greedy search algorithm, it operates like this. It does multiple passes on the vtree, bottom-up passes, and when it's in a particular node, let's say X in this case, it will identify a left linear fragment which has X as its root. And in this case, this happens to be the following. And then it will try to search all possible states or all possible 12 vtrees of that particular fragment. And then it will go and identify a right linear fragment which has X as its root. And in this case, that happens to be this. And again, it tries to search all possible 12 vtrees of that particular fragment. And that leads to a total of 24 vtrees that are explored in this case. And what the algorithm will do is will greedily accept the best of them, and that is the one that leads to the SDD with minimal size. And then it will just keep moving up to the parent of X. As I mentioned, this algorithm does multiple passes on the vtree, and if the change in size of the SDD between one pass and another is small enough, then it will just terminate. And that particular threshold for termination is something that the user can set. The other thing that this algorithm does is it has a heuristic for trying to examine the vtree and the corresponding SDD and make a guess on what parts of the vtree may not change due to the search process. And in that case, it will simply skip those during the search. So it may not actually explore every node in the vtree to search these particular 24 states. Now, the one thing that I should emphasize here is realize that bullet 2 and 3 say try enumerating, try enumerating. And the reason for this is the limits. Remember that vtree operations are limited by time and space. So it's possible that we may not actually be able to explore all these 24 different vtrees. So that's basically it. This is the vtree search algorithm. It's pretty simple now, given the vtree abstraction and all of the support that the SDD package gives in this regard. Let me mention here some important opportunities that people can contribute to as far as improving the SDD package. So one of them is to add more search algorithms. If you look at packages for OBDDs, for example, you're going to find a relatively large number of algorithms or search algorithms for finding good total variable orders. The SDD package only has one of these, so there's room for adding more. The other thing that can be done is triggers for vtree search. So when you're using vtree search in the context of bottom-up compilation, there is a question of when do I trigger vtree search. So as I mentioned, one of the methods is to look at the size of the SDD, and if it doubles in size since the last search, then we invoke search. That's pretty primitive. There could be more sophisticated methods. Actually, the SDD package has a little bit of a sophisticated method for doing this, but one can improve that significantly because the way or the time to trigger vtree search can be significant in terms of the impact on the efficiency of bottom-up compilation. And the last or the third way that one can contribute to the SDD package is perhaps adding methods for statically constructing vtrees. Currently, the package only have simple methods that do not even analyze the structure of the input, just have like left linear, right linear, vertical, random, balanced. But one could add static methods that actually analyze the input, let's say of a CNF or a DNF, and then tries to come up with a more informed vtree to seed the bottom-up compilation process. And finally, I should mention that this process of scheduling apply operations, which come up, for example, when compiling CNFs or DNFs to SDDs, that could be critical. The order in which we compile the clauses basically dictate here the schedule for apply operations. So here's the link for the SDD package. It's available online. It's written in C. It is open source, and it does have code for compiling CNFs and DNFs into SDDs, and that includes a particular heuristic for scheduling apply. That is a particular heuristic for deciding the order of clauses when compiling a CNF, or the order of terms when compiling a DNF into an SDD. And the SDD package comes with two manuals, one for beginners and another for more advanced users that give a detailed exposure and explanation of the API. And if you want to read more about the underlying theory behind vtree search, and these particular operations and how they work, then you can consult this particular paper, which appeared in AAAI 2013, and it's in this paper that these operations of left rotate, right rotate, and swap were introduced, and where the details of how each operation leads to changing the SDD. All of that is detailed in this particular paper. And that basically concludes this tutorial, and thank you.